Welcome to The Explainer. Today, we are unpacking a massive hurdle in the world of mixed reality, or XR. If you've ever put on a modern headset, you've probably felt that amazing magic of seeing digital objects perfectly interact with your real physical room. But here's the really exciting challenge. How do we make these headsets map our rooms instantly and in high detail, without completely killing the battery or making the device literally red hot on our faces? Well, I recently stumbled onto a groundbreaking system called Ada that solves exactly this, and it is fascinating.
Here's our quick roadmap for this explainer. First, the spatial computing challenge. Second, enter Ada, offloading the work. Third, Ada's clever engineering hacks. Fourth, the performance payoff. And finally, number 5, the future of XR.
Section 1. The Spatial Computing Challenge. Friction in XR. Let's really dig into the core bottleneck that is holding back modern mixed reality right now.
I want you to think about this for a second. When you tell a headset to place a virtual object in your room, how does it actually know exactly where your coffee table is? There is a ton of invisible magic required for spatial computing to work seamlessly in your living room, and it has to happen in the absolute blink of an eye.
Take this teapot, for instance. When you say, place a teapot on the table, the XR app doesn't just magically do it. It actually has to constantly ping the system in the background, asking for the absolute latest reconstructed 3D map of your room. It needs to understand the whole scene, find the table, and only then can it accurately place that virtual teapot so it doesn't just awkwardly float in midair. The industry actually has a formal term for all this heavy lifting. It's called real-time scene provisioning. It's just the continuous background process of rebuilding the 3D geometry of your room and delivering that data to the apps that need it. Your headset is literally constantly doing this while you play, work, or just browse. But the problem is how we've been doing it. The old way, like with prior state-of-the-art systems, tries to do all this brutal processing right there on the device. And because the headset has limited computing power, it's forced to use low-resolution data just to stay fast. So what happens? You get coarse, chunky meshes, lagging updates, and a massive drain on your battery. And honestly, nobody likes getting booted from a session right when it gets good. The ideal state, obviously, is lightning-fast updates with incredibly high fidelity, all while barely sipping power. Section 2. Enter Ada, offloading the work. This is where we introduce the real hero of our explainer. Ada completely flips the script. Instead of forcing that tiny mobile chip inside your headset to do all the grueling math of reconstructing a 3D room, Ada just offloads it. It captures the raw depth data from your headset, fires it over your local network to a powerful remote server, like that gaming PC already sitting in your house, lets the server build the highly detailed 3D mesh, and then just beams the updated pieces right back to your headset. Section 3. Ada's clever engineering hacks. Because, as you can imagine, moving massive amounts of 3D data back and forth wirelessly usually completely chokes a Wi-Fi network. Ada pulls off this data-moving magic trick using 4 distinct, incredibly clever engineering innovations. We have efficient depth encoding, decoupled processing, extraction-aware scene management, and real-time mesh compression. Let's walk through these one by one because this is where the pure genius of the system really shines. I absolutely love how Ada handles the raw depth data coming from the cameras. So 16-bit depth data is incredibly heavy. And standard hardware video encoders, the fast ones built into almost all our devices, usually only accept 8-bit formats. So Ada uses this brilliant suitcase packing trick. It essentially chops that heavy 16-bit pixel into 2 lighter 8-bit pieces. It packs the most important half perfectly using lossless encoding to save the exact geometry and compresses the rest with lossy encoding. It sneaks both of these 8-bit streams right through those lightning-fast standard encoders, slashing bandwidth without losing accuracy. It is such an elegant solution. The second hack is all about not waiting in line. Older systems tightly coupled the process of fusing the scene together with the process of extracting the mesh for the app. It created this huge sequential bottleneck. Well, Ada just decouples them. It lets the system furiously reconstruct the high-resolution scene in the background at super high speeds, while only extracting the 3D mesh updates when they cross a certain threshold or when the app actually asks for them. Now, once the server finishes building that new geometry, the third trick kicks in. It doesn't send the whole room back to the headset. That would be a complete waste of bandwidth. Instead, it only sends the small, partial mesh chunks of what actually changed. Maybe you moved a chair or your dog walked in. The headset catches these tiny updates and seamlessly merges them into its existing cache. It's incredibly efficient and totally vital for keeping battery consumption low. And the final piece of the puzzle is how those partial updates are packaged. Because even small 3D meshes can be surprisingly bulky. Standard mesh compression is great, but it runs on a single thread and takes way too long, like over 60 milliseconds just to compress one update. Ada fixes this by slightly relaxing a process called data deduplication. This allows it to chop the mesh into smaller chunks and compress them all at the exact same time across multiple CPU cores. It completely slashes the delay, meaning the data flies out of the server and back to your headset almost instantly. Section 4. The performance payoff. So all these clever hacks sound amazing on paper, but what do they actually mean for the person wearing the headset? Let's take a look. Just look at this stark visual difference here. On the left, using old coarse 6-centimeter voxels just to try and keep up with real-time demands, the system totally misses the fine details. I mean, you can barely tell there's a chair there. Contrast that with Ada's high-fidelity 2-centimeter mesh on the right. Because Ada let the remote server do the heavy lifting, it has the computing muscle to capture perfectly fine details, like the thin legs of the chair and the exact shape of objects. And it doesn't just look better, it is blazingly fast. Compared to the prior state-of-the-art system running locally, an on-device version of Ada was up to 6.8 times faster at delivering these high-fidelity updates. That means literally zero noticeable lag when your app asks for the room layout. But here's the crucial point for anyone who has ever had their headset die mid-session: battery life. By using the fully distributed Ada system, sending the hard work to the server and only doing the lightweight merging on the headset, Ada actually lowers the incremental device-side power consumption by a massive 24% compared to the next best alternative. When you put them side by side, the next best on-device system pulls about 2.61 watts just to manage the scene, while distributed Ada pulls only 1.99 watts. Now, half a watt might not sound like a big deal, but in a tightly packed wearable strapped to your face, less power means significantly less heat generation, a way more comfortable experience, and greatly extended playtime before you have to plug back in. Section 5. The future of XR. Let's zoom out and look at what all of this means moving forward. The innovations packed into Ada prove for sure that we don't have to compromise anymore. We can have highly detailed instant spatial computing and lightweight, cool-running headsets. By brilliantly utilizing remote servers and local networks, we are paving the way for the next generation of wearables. So I want to leave you with this to think about. What entirely new experiences become possible when our XR glasses finally stop trying to be a supercomputer strapped to our faces and instead act as a lightweight, beautiful window into a computationally infinite world? Thanks for joining me on this explainer. I really can't wait to see where this technology takes us.